Okay, so last time we talked about cell complexes, and we got introduced to a couple of different concepts, like the Euler characteristic of a cell complex. And we learned some terms like the skeleton or boundary, and got a basic feel for the sorts of things that we're going to want to try to compute with. So in a sense, cell complexes are kind of like the sort of end of like the mathematical fundamentals that we need to really do computational geometry. So basic structures that we care about in geometry, we have sort of points, lines, and planes, then ultimately polytopes, and then cell complexes, which occur as the boundary of polytopes, but can also just occur on their own, as things like planar subdivisions or maps or other types of structures. So I do want to quickly finish up a couple of things on the Euler characteristic and also correct a slight mistake that I made yesterday. It was a mistake of notation. So if we remember the Euler characteristic of a cell complex delta, or x, or we'll write it like that, yeah, because I think that's what I used. This is just the sum, or this alternating sum of all of the entries in the f vector of x. So from 0 to d minus 1, negative 1 to the I, f sub I. And we'll pretend that this f sub I takes cell complex in there. We also saw that this thing was related to this differential, or to this linear operator, right, or this linear matrix delta, which we called the differential. And I said that this was equal to the rank of the differential, but that's actually the wrong term. It's actually called the index, right? So this is this may have confused people or not, I don't know. But if you've ever heard this term index, right? It's the index of delta, and this is equal to the rank of delta minus the co-rank delta. So this is basically the dimension of the image minus the dimension of the kernel of an operator. So this is sort of an invariant. For most matrices, the index of a matrix is going to be 0 because vector spaces tend to be sort of flat or contractible in a sense, and so their index is 0. But for polytopes, this thing actually turns out to be equal to 2 if d is odd, or 0 if d is even. And that's because this delta here, in a sense, can kill off these higher dimensional cells, right? So that's sort of the issue with that. So, OK. So that's the basic idea behind the Euler characteristic. And we basically proved this, or kind of proved it, for simplicial complexes. But I claim that this result is actually true in much more generality. So this definition of an Euler characteristic is actually independent of whatever cell structure you pick on polytope, and it will actually hold for any polytope just the same. And more interestingly, it actually turns out to be a homotopy invariant of a manifold. So we'll say that, first of all, we'll say that given some arbitrary manifold, don't worry about what this word means for the moment, M, this will actually be equal to any other manifold N if M is homotopy equivalent to N. So I'm not going to define what these words mean. It sounds probably like some gobbledygook, but here's kind of the mental picture, is that if you can take any shape and if you can either stretch it or squish it, but not tear it, and deform it into another shape, then we'll say that those two shapes are equivalent. So maybe you've seen this joke before, right, where you say a mathematician, or a topologist is a mathematician that can't tell the difference between a donut and a coffee cup. It's because if we imagine if we took this donut and then sort of pulled in the edge here so that maybe it looked like this, and then kind of kept the other side here and then started putting a little divot in it, and then kind of stretched it all the way out, then we could end up with something that looks just like an actual coffee cup. Right? So a donut could be deformed into a coffee cup by stretching it and squishing it. And the Euler characteristic for this donut, the way that you would construct it, is you just throw any old cell complex you like on it, because it doesn't matter, in a sense, which cell complex you pick. And then when you're all done, you can calculate this number, right, which is actually the rank of this differential here, or the index of the differential, not the rank. Right, I said rank last time. That was wrong. But that number will basically be invariant for whatever cell structure you pick. And it's also the same for any two shapes which happen to be homotopy equivalent to one another. So I said that this is invariant under different cell structures. And to give you some intuition for why this would be true, I can just do a couple of examples, right? I mean, this is by no means a proof. But for example, if I started with, say, maybe an edge in some cell complex, and I wanted to remove that edge by collapsing it, then I claim that doing that edge collapse doesn't change the Euler characteristic. So here's a picture. So imagine I have two faces here, and then there could be some other rest of the space. And these are just faces, so they're filled in. So if I take this and I collapse it into something like this, right, by basically taking this edge and then pushing it down onto this vertex, then what happens here is, well, so for starters, I lose this vertex. So I'm going to go one down on V. I also lose this edge, and this edge. So 3 edges go away. And I lose 2 faces. So that's that. And if I sum these up, using the Euler characteristic, I get -1 vertices minus -3. So it's +3 for the number of edges, and then -2 for the number of faces, which is equal to 0. So there's no net change in the Euler characteristic under this type of operation. Similarly, if I take a face and I split it so this type of operation is called an edge collapse. We may see these later if we get to it. Another related operation is called barycentric subdivision, which is where we just poke a hole or stick a vertex right in the middle of a face. So here'd be the picture. I start with some face, and I just stick a vertex right in the middle of it. So I end up with a new face that looks like this, or 3 new faces. And so if I look at the change here, I have 1 extra vertex. So I get 1 additional V. I have 3 more edges, and I have 2 more faces. So again, if I plug these things into here, I have 1 minus 3 plus 2 equals 0. So again, no change in the Euler characteristic. And you can do this for other sorts of operations, like deleting an edge and merging 2 faces together, or collapsing a face onto an edge. Right? That is also a valid operation, or subdividing an edge, and so on. So this, again, doesn't constitute a proof that this thing is invariant under the cell complex structure. That would actually be a more involved thing to prove. But it should at least convince you that it doesn't matter what cells you pick. All that matters is the underlying space of the cell complex. Another important property of the Euler characteristic is that it obeys an inclusion-exclusion rule. So it's sort of like it behaves like cardinality in this way. So here's the picture that we have. So if we take 2 different sets, right? So now I'm not talking about a cell complex, but I'm just talking about sets right now. So if we just take 2 manifolds and we union them together, then this is going to be equal to the Euler characteristic, or the sum of their Euler characteristics, minus the Euler characteristic of their intersection. So this is called an inclusion-exclusion property. And in this sense, you can think of the Euler characteristic as behaving something like cardinality for a set. So if you imagine that this was like, say, a finite set, right, then the Euler characteristic would just be equal to, would in some sense act like cardinality of them. And actually, another trivial property here is that if you take the Euler characteristic of a point set, then you get 1. And so it actually turns out that this property, and the homotopy invariance is actually sufficient to completely determine the Euler characteristic. So we counted it in this way, right? But you can actually derive it in another way. So it turns out if you combine this property, the property that the Euler characteristic of a point is equal to 1, and the property that g of s equal t if s is homotopic to t, right, which is a term I didn't define. But these three properties are actually sufficient to completely determine this. Right, so that's yet another perspective on the Euler characteristic. It's a slightly more abstract way to define it, and perhaps more appealing from a topological perspective. But this one's way easier to calculate, and it's also easier to prove that it works for polytopes. So that's the one we picked. This one would probably be the definition you would see in a course on algebraic topology.
So quick question. So the original formula, we showed that it's 2 if d is odd and 0 if d is even. Is that for just any?
It's only for polytopes. So yeah. So here's another point that I should make. So this is the general version for manifolds, right? Now the thing is that for polytopes, what we're actually looking at here, right, is the boundary of the polytope, because we're going all the way up to the d-1 cell. So what's really going on is that you can imagine that we have a sphere. And so this is actually just calculating the Euler characteristic of an n-sphere, or of a d-sphere, actually. So this is basically equal to g of sd. All right, so we're just looking at the boundary of a d-sphere. So it should actually be a d-1 sphere following this convention. All right, so in the case, so for example, you can say that the Euler characteristic of a circle, right? This is not 0. It's actually a circle is equal to 0, right? Coincidentally. And the Euler characteristic of a 2D sphere is equal to 2, right? So similarly, if we take the Euler characteristic of 2 points, which is actually a 1 sphere, right, then this will be equal to 2 again, because we have 2 points, right? So we could actually prove that using just this rule and this rule, right? So that's easy to check. So this just is the general pattern for calculating the Euler characteristic of a sphere. And that's where we get the Euler characteristic of a cell complex for a polytope. So that's Euler characteristic in a nutshell. One consequence of this is that it constrains the f vector of polytopes to sit within a plane, right? So we know that if we have, an f vector, right, for a polytope, excluding the -1 in the d cell, right, then this now has to live within an affine plane that is determined by the equation the Euler characteristic is equal to 0 or 2, depending on the dimension. All right, so that actually turns out to be as good as you can get for a general cell complex. But for certain special kinds of cell complexes, you can often say a little bit more than that. And one important example of this is a simplicial complex. So I'll just say this right now. So first of all, first observation is that g of x equals 2 or 0. Otherwise, right? It's an affine plane. And here's a proposition. I won't prove it. But this turns out to be the only constraint for a general cell complex. So this is actually the affine hull of all f vectors. All right. So we can say that these things live in at least a d-2 dimensional space, right? But in the case of simplicial complexes, we can actually say a little bit more. So if we know that every cell is going to have exactly d plus 1 points in it, or each k cell has exactly k plus 1 points, then that can simplify some of our calculations, and it can actually tell us a little bit more about what's going on. For example, so I'll now make this very concrete. So let me erase this. I'm going to need more space here. So OK, in 3D, here's something that happened. So for simplicial, so not polyhedral cell complexes, can often say more. Example. So here's the case where d equals 3. So we're looking at the boundary of a 2D sphere or a 3D or a polytope embedded in 3D space. So here, if we kind of look at some patch of the boundary, everything is going to be triangle. So we'll say every two-face, we'll say triangle, touches exactly 3 edges. Right? That's always true. And similarly, every edge touches exactly 2 faces. So this is a one face. So another way that we can say this, right, is that in 3D, right, not generally true in arbitrary dimensions, we have this additional constraint that 2f1 is equal to 3f2, right? So this is a special equation that's only true in the case of simplicial complexes for 3 polytopes. And this is actually independent of the equation f0 minus f1 plus f2 equals 2. So we have these 2 constraints here. And this actually is enough to basically determine the number of faces in the polytope given the number of vertices. So how do we solve for this? Well, we can just multiply through by 2 here, right? So if we do this, we get 2f0 minus 2f1 plus 2f2 equals 2. Substitute this in. So these 2 constraints imply that if we have 2f0 minus 3f2 plus 2f2, this is equal to 2. So we have 2f0 is equal to 2 plus f1, or f2. Did I do that correctly? Minus 3 plus 2. Yeah, I think that's right. Oops. I want to make sure I have the right page here so I don't do a typo. Just double check. Yeah, I think this is correct. So let's check it out. So let's suppose I have a tetrahedra, right? So I'll have 4 verts, so that's 4 equals f0, 6 edges is equal to f1, and then 4 faces, which is f2. So if I plug that in, I get 8 is equal to, nope, that's not right. I made a mistake. Where did I make a mistake? Oh, yeah, this should be a 4. Right, that's where I went wrong. OK. All right, that's the typo I made. So OK, now this is right. So we have 2f0 is equal to 4 plus f2. Right, so if we look at this, what this tells us is that the number of faces here is going to be about on the order of 1/2 of the number of vertices plus a factor of 4. Right? So the conclusion to this is that in 3D, convex hulls are basically linear in the number of vertices. Right? So that's the moral of the story. So we'll say in 3D, convex hulls are order n, right? So that's the conclusion of that, right? Is that the f2 vector, right, which is basically the d minus 1 faces, and that's also the size of the convex hull, is bounded directly by the number of vertices. In fact, it's completely determined. So if you have any triangulation of n vertices, you're always going to have exactly n over 2 minus 4 faces. Right? So that's the upshot of that. OK. So can we generalize this a bit? So the key thing was that we had this extra constraint here in 3D because it was a simplicial complex. And it turns out that, yes, you can, and it looks a little messy. Right? And this is given by a set of equations which are called the Dehn-Sommerville equations. So this is kind of a generalization. And this only applies to simplicial complexes, not arbitrary polyhedral complexes. Of course, in general, for an arbitrary V polytope, its cell complex, or its on its boundary, is almost always going to look like a simplicial complex. And so it will usually end up being something like this. So here is sort of the Dehn-Sommerville equations. And I'm just going to write them down. I won't try to prove this because these things will probably not have to use them directly too much. If you do higher dimensional computational geometry, which would basically be beyond 3D geometry, then you'll see these things much more frequently because they really start becoming important in 4 dimensions and then higher. And so these are the then. And there are a few cases where we'll need to do something, or we'll need to prove some bound that involves lifting things up into a higher dimensional space. And so we'll just refer to this type of a result, but we won't have to, like really kind of dig into it too deeply. So these are the Dehn-Sommerville equations. Right? And we'll say for simplicial complexes, not general cell complexes. So this is basically a set of D equations, right? So D minus 1 equations. That's right. Hope I have this correct. So I'll say for -1 less than or equal to k less than or equal to D minus 2, we have that the sum from j equals k to D minus 1 of -1 to the j times j plus 1 choose k plus 1 of f sub j is going to be equal to -1 to the D minus 1 of f sub k. So this is a system of D minus 1 equations. And if we actually plug in k equal -1, this reduces to the Euler characteristic. So in some sense, you could think of this as sort of the extension of the Euler characteristic, but only for simplicial complexes, right, when it works. It turns out that you would think this basically completely constrains all of the f vectors so that there's only one parameter, but there's actually a lot of redundancy in these equations. It turns out that the actual number of relevant variables for the f vector in D dimensions is actually D over 2, right? So the number of actual degrees of freedom is floor of D over 2, essentially. So it turns out that in 1D, well, this is actually, so here we'll basically just go through by dimension. And then these will be f vector degrees of freedom. So in 1D, well, it's completely constrained. F vectors are trivial, right? In 2D, 3D, we actually only have 1 degree of freedom, right, for simplicial complexes, which is basically the number of vertices, or you can think of it as the number of edges or triangles, whatever. One component, all of them. Turns out in 4D and 5D, it's a lot trickier to get this kind of description. You have 2 degrees of freedom. And this continues on, so 6 and 7, you have 3 degrees of freedom, etc. So this is partly why really high dimensional convex hulls get a lot trickier, is that it's even harder just to come up with topological invariants that describe them, right? So the nice thing is that in 2D and 3D, things tend to be much better behaved. But once you go to 4, things start to get a little bit weird, right? Related to this idea is, and the next kind of interesting result on higher dimensional convex hulls, is this result called the upper bound theorem. So in 2D and 3D, we know that because there's only one degree of freedom in the F vector here, you can only have a linear number of elements on the convex hull of some polytope. But in 4D and 5D, we have two variables, so we'd wonder how many degrees of freedom are kind of left over there. All right? The intuition is that it should probably be about quadratic, right? But we can actually prove this somewhat more rigorously, which I will do again by just appealing to another result that we won't actually go into how it's proved. But yeah, it's not so bad. By the way, the proof of the Dehn-Sommerville equations is pretty straightforward, actually. It's not too hard. You can look it up in a book, and you can follow along with it. We're just not going to need it right now. The other interesting theorem, and this is one that we will use a lot, and we won't bother to prove it, is the upper bound theorem. And the proof, there's multiple ways to prove it, but probably the easiest way to do it is to use this technique called shelling, which you can also use to prove the Dehn-Sommerville equations too, and also derive the Euler characteristic. So the upper bound theorem, this basically gives us a bound on the entries of the F vector in terms of the lower dimensional entries of the F vector. So you can think of these as inequality constraints on how big the F vector can possibly get. And the basic idea behind the upper bound theorem is that there is this sort of pathological curve, which you can think of as generating the largest possible convex hull for a given set of vertices. And so this curve can actually be constructed explicitly, and we'll actually use this curve a lot, right? It's called the moment curve. So here's the idea. So the basic result of the upper bound theorem can be summarized by saying the moment curve has the largest F vector. So what is the moment curve? Or the cyclic polytope. I should actually write it this way. Cyclic polytope. So what is this thing, the cyclic polytope? Well, the way it's constructed is as follows. So we start from this thing called a moment curve. And the moment curve is a parametric curve in R to the D. And we're going to write it with mu as the symbol here. And so it maps points in R to points in R to the D according to the rule that mu of t is going to be equal to t squared, t cubed, and so on, all the way up to t to the d. So if you've ever taken algebraic geometry, you've probably seen variations of this, where if you've ever had to work through the exercises in Hartshorne or something like that, they usually tend to spend a lot of time on this twisted cubic curve, which is actually just the moment curve in the first three variables. So that's the idea. Now here's the interesting thing about this, is that if you take any n points on the moment curve, right, in RD, these points will be completely linearly independent, right, because they're all just generated by squaring and cubing variations of them. So here's the sort of proposition. So we'll say any n points on mu are linearly independent. All right? And so with this idea, we can now construct a collection of endpoints which are all linearly independent. And moreover, they're all actually going to sit on the convex hull of some horrible polytope, right, which will have lots and lots and lots of faces. And this is called the cyclic polytope, which is sort of the extreme, crazy degeneracy that you should often try feeding into your programs anyway if you're trying to come up with good test cases to run them on. And this is the cyclic polytope. So here's how this is defined. We'll say take t0 less than t1, or less than, we'll just, etc., all the way up to tn minus 1. So just n different points in R. And then we're going to define this polytope, C and D, to be equal to the convex hull of mu of t0 mu of t1, etc., all the way up to mu of tn minus 1. Right, and so this is the crazy polytope, CND. And it turns out that you can pretty easily calculate the number of entries on the F vector, or how big the F vector is of this thing, right? So I won't do it right now, but I'll just say that this is kind of the result that you get. So we'll say for 0 less than or equal to I less than or equal to d over 2, the ith f vector, or the ith component of the F vector of C and D is going to be n choose d plus 1. Right, and then the Dehn-Sommerville equations allow you to determine the rest of the components of the F vector from that result. But the moral of the story, though, right, is that if you take the d minus first component of the F vector in terms of the number of vertices, n, then it will end up being n to the d over 2, right? So that's the result. So this is the big conclusion here. Right, so I'm going to erase this stuff here. The Euler characteristic. So here's the conclusion. Convex hull of n points in d dimensions is at most or we'll just say it's in order n to the d over 2 rounded down. So that's the idea. So it turns out that, you know, in 2 and 3D, the size of the convex hull is linear. In 4D and higher, we end up with quadratic and then cubic and then higher order polynomials. And this is, in a sense, why convex hull algorithms tend to fail or be impractical in dimensions greater than 3. So we're really going to be mostly focused on calculating convex hulls explicitly when the dimension is small, because this is really the only case where it actually makes any sense to do so. So that's the upper bound theorem. Now, you can, of course, consider calculating higher dimensional convex hulls. Maybe you want to visualize it or something like that. But just keep in mind that you're going to be dealing with things which are guaranteed to be superlinear in size. So, OK. So now we have some idea of how big cell complexes are. And you know a couple of different properties about them. I want to say a few words about how duality looks for cell complexes. So we'll erase this thing. No, it's an upper bound, because they can be smaller than that, but they'll never be larger than that. But of course, it gives you a bound on the running time, right? Because you can now always construct some input for your convex hull algorithm, which will require at least omega n over d over 2, because that's how much your output size is going to be. But you could have output which is smaller. So this is the other reason why output sensitivity becomes very important, because maybe the output of your convex hull algorithm could be much smaller than the size of your input. So if you're constructing something with n vertices as an input, then the output could potentially be as bad as n squared, right, in 4D, for example. But it might actually be a lot smaller. So remember, in 2D convex hulls, we had things like gram scan or these more efficient algorithms like Jarvis March, where gram scan always used, you know, basically n time or n log n time in order to compute the convex hull, whereas the Jarvis March uses like n times h time, where that h is the size of the hull. So if you allow the size of the hull to be a parameter, then maybe you won't actually hit this worst case, you know, n squared size hull. Maybe it'll be much smaller, right? But we'll see some algorithms for doing this in 3D convex hulls when we come to them, which we will probably not get to today. We just have to finish off cell complexes for now. So right, so let's talk about duality. So duality has a fairly concrete interpretation in terms of what happens to the cells of a cell complex, which is that it swaps the d cells with, or the k-dimensional cells with the d minus k-dimensional cells. So here's sort of the picture. Right, so if we start, so imagine that we're looking at the boundary of a polytope here. So we'll say that these are all triangles, or let me draw this over. Something looks like a little more interesting. So suppose these are points on the boundary of some polytope, or maybe they're just points in a plane. I don't know, maybe I'll put another point here. All right, so the dual of this cell complex will map each of these faces of the complex to some vertex, and then each vertex to a corresponding face. And it'll flip each edge. So if I take a point here, point here, point here for each cell, this becomes the dual of each face. And then for the edge, I'll just connect them along these dashed lines. Going off to infinity. Right? And then these loops which are left are basically the faces which are surrounding each vertex. And so in general, when you take the dual of a polytope, you might have something where you have, say, like this skeleton x0 contained in x1, contained in x2, etc. And then the dual will basically transform this into some, x star d minus 1, which contains x star d minus 2, which contains, etc., going off to the other direction. And then we'll have maybe, like, say, an empty set here. And then this will be the polytope P, which contains them. So this is sort of how duality draws this. So we can think of this as basically, each. So in 3D, well, let's do it first in the trivial case. So in the trivial case of 2D, right, imagine you have like a loop like this. Well, each edge will become a vertex. And then each vertex becomes a face. So we have this map where we basically swap vertex to edge, and then edge to vertex. And then in 3D, well, we've already seen kind of what it looks like in this picture here, but just for the sake of completeness, so we'll map vertices to facets, basically three faces, so polygons, right? Whoops. Edges just get flipped, so each edge maps to another edge. And then these facets will get turned back into vertices. So that's a geometric picture of what happens in duality. We'll return to this later in more detail, but I just want to sketch out what happens. One important point, though, is that it doesn't change the Euler characteristic of the cell complex when you take a dual. So if we swap these things around, then the resulting alternating sum that we'll end up with will actually be completely unchanged. So it will basically leave the Euler characteristic completely invariant for this space. And we'll come back to this later. OK. So let me check how I'm doing for time right now. Oh, wow. Yeah, I'm doing really good. So OK. So with the rest of this lecture, I'm going to talk about data structures for storing cell complexes. So this is going to be pretty important when we start implementing 3D convex halls and start actually trying to do different geometric computations on cell complexes, is that we need some data structure in order to actually get a handle on these things and start doing real work with them. So these are now we come to data structures. In some sense, the general approaches to this don't look that different than the general approaches for storing graphs as data structures. And it's probably intuitive that that should be true because cell complexes are, at the end of the day, just higher dimensional graphs. So here are sort of a couple of things that we might like to have, right? So some desired properties of any kind of data structure, really, right? But the first thing is that we'd like this to be, in some sense, informationally complete, or we'd like to be able to represent any valid cell complex within this data structure such that there's no ambiguity of it. So we want to be able to represent any valid cell complex. In addition, we might want it to be canonical, right? So we would like to perhaps have some normal form for a given cell complex, so we can, decide if two cell complexes are identical to one another up to some condition, right? So the easiest case is if we happen to have all the vertices labeled, then we'd like to say that for this given vertex set, these two cell complexes are equal. So we'd like to have it maybe be canonical or normalized. These are just general considerations for any data structure. And then finally, we'd like to have efficient queries, so that operations on it would be fast. And then maybe efficient updates. So perhaps we can make it. These are just, pretty broad considerations. It turns out, well, this is pretty much easy to do. We can easily get data structures that fall somewhere on this range over here of different properties. But to really get into this, we actually have to say first what sorts of queries we care about, right? And then also what sorts of updates we're going to care about. So here are the two big ones. Is we want to nail down the queries, and we want to nail down updates. So topological query, or what are the kind of queries that we would like to execute on a data structure for a cell complex? Or what sorts of things do we care about? So this is the idea. There is, broadly speaking, two different types. So we have topological queries, which only look at the combinatorial structure of the cell complex. That is the incidence between the cells and which ones are contained in one another. And we have geometric queries. And these would be things like, tell me which point contains a given cell. Or if I take an arbitrary point and query it against the cell complex, locate all cells which happen to be contained within a ball or some region, right? So these things we'll call basically point location. Although secretly, these are pretty much linear programming, right? So all the geometric queries we care about will turn out to be some variation of linear programming or another, really. The topological queries that we'll care about are going to be incidence and adjacency, which is, in a sense, very similar to incidence. So we can imagine that if we have, say, two cells here, right, or maybe if we have a vertex, perhaps you'd like to say, OK, if I pick this vertex, give me the list of all faces which happen to be incident to that vertex. Or if I take a face here and one of the edges of the face, I'd like to say, OK, give me the face opposite on that edge, right? So I can walk along it. For example, to illustrate how this could actually be useful, suppose we want to do, say, point location in some map, right? Well, we already kind of know a technique for doing this, right, from linear programming, which is that if you imagine that, OK, suppose I want to locate the cell that contains this point, right? Well, what I could do is I could just start from a random cell and a random point over here, and then just say, OK, I'll look at this cell, then which of my neighboring cells happen to be the closest to this point, then walk to that cell, then walk to that cell, and walk there until I get there. Right? I mean, that's basically what the simplex method does. So in some sense, if I have at least the topological information, I could certainly use that to speed up this process of, say, locating points inside there. And we'll return to this technique later on. This is actually called jump and walk. It's a method for performing point locations and maps. Right? It's not the fastest algorithm. There are ways that we can actually do even better than this. But in higher dimensions, it turns out to be pretty damn good, similar to how the simplex method turns out to be pretty good when you go to higher dimensional spaces. So the focus for the data structures that we're going to talk about today is not really these geometric problems. Right? So this will be in a later lecture. So we're going to do this later. And these problems are actually a little bit harder, right? So we're going to have to think about those much more carefully. This is what we're going to do today. So we're going to focus on these topological queries, right? So in more detail, the main topological query that we're going to care about is an incidence query, which we'll define as follows. So we'll basically define the set I sub j of f, which is equal to the collection of all cells G in the J skeleton. So it's the collection of all cells such that G intersect F is not empty. So that's the simple idea, right? The standard example, of course, is if you take a vertex and you want to find all of the faces which contain it. Or maybe if you take a face, you want to find all of the vertices within that face. Right? Or if you have an edge, you want to find all of the triangles that happen to touch that edge, and so on. So this is the main query that we're going to care about trying to optimize. We'll also define a related quantity called the degree, or the j degree of a face, which is just the cardinality of that set of F. All right, sometimes they write this phi sub j, I don't know, there's different notations. It's basically the degree. So if you take a vertex, the intuition is for graphs, the degree of a vertex is just equal to the 1 degree. You know, and so you can think of this, you know, in terms of graphical data structures if you like. It's not too different. So, all right. And then for updates, what we would like to do is be able to add or remove a cell from the complex. That'll be our simple update. So we'll just think of, you know, either deleting a cell or inserting a cell. Right? And then with delete and insert, you can implement things like edge collapses or other different topological operations on a cell complex in terms of a series of removals and additions. So, OK. So how do we realize these incidence queries, right? Because if we can do these incidence queries, then we can start doing a lot of interesting stuff. Like, for example, you can find all the adjacent vertices to a face, or adjacent faces to a face, etc. Well, here's the simple data structure. Which we're just going to call a cell list. It's basically the same thing that we have for storing a graph as just a list of edges, right? So we're just going to think of this as a list of cells. And we could sort it if we wanted to normalize it, right? So we can basically just sort each cell and then sort all of the cells lexicographically, given a total order on the vertices, and that would give us a canonical representation for a given vertex set. The nice thing about this data structure is that it's relatively compact, right? So the storage is basically order the number of cells times, or it's basically the sum of the 0 degrees, right? So we can basically think of this as the sum of the 0 degree of each f. So sum over all f in x right? Which, if we assume that this is relatively bounded, or it's constant, right? So that, in other words, no cell ever gets too large, this is basically order n, which we're going to take to be the number of cells. So that's pretty much as small as it gets, right? You can't really store one of these things any tinier than this. The problem, though, is that queries are equally bad. So the easy case is if you have a cell and you want to find all of the lower dimensional cells which happen to be properly contained inside it. That would just be a constant time operation, or it's just going to be order the size of the cell. So for example, I0 of f is constant. But generally, if we take j of f is order n, right, for any other value. So if you wanted to say, like, OK, find all of the edges which happen to be incident to some vertex, well, now you have to do a search through this entire list of all of the cells in order to find those edges, and that's going to be pretty bad. So queries are pretty slow, but it's pretty easy to add and remove stuff. I mean, if you imagine storing these things in a linked list or a map or something, that's just like a constant time operation to add or remove. So updates are cheap. You can basically do it in constant time. All right, so that's that. It's kind of the non-data structure, but it can be valid for small input cases, right? And if you're willing to basically pay this cost of doing an order n search, OK, no big deal, right? I mean, you can just do it. And probably if you're going to try to transfer a cell complex like over a wire, or you want to basically like take the data from some mesh and then serialize it, you'll probably serialize it to this, right? So this is sort of the standard interchange format. But it's probably not the one that you would want to use in memory, because oftentimes we're going to need to do lots of queries on the cell complex. And so we'd like to maybe cache this thing or convert it into some other representation where these queries can be executed more efficiently. So the other sort of obvious data structure is to just generalize an adjacency matrix. So the adjacency matrix for a graph is just this enormous, n by n matrix. Yeah?
So couldn't you just do the same thing as a cell complex? Just store kind of like a back pointer of whatever it's also contained in, and just like.
Yeah, we'll come to this in a moment, right? That's the next thing that we'll do after this. But yes, there are, in fact, there's actually an enormous number of data structures for doing this in high dimensions. But today we're going to go through first a couple of very easy ones, and then we'll see some very interesting ones that will allow you to do this fairly efficiently, right? But that's the dumbest data structure. So yeah, before getting ahead of ourselves, though, we'll just say one more thing. So we have adjacency matrix, right? Or it's actually an incidence matrix. Again, this is another one of these, this is a data structure that you should pretty much almost never use realistically, but it's probably worth mentioning it, right? It's not something that's actually practical, but store enormous matrix of incidence. I mean, it allows us to check. Basically, the advantage of this is that we can test if G is contained in IJF in order 1 time. But the storage is terrible. So the storage is going to be quadratic, which is really bad. And updates are really just not going to work. So this is pretty much terrible.
So n is just like
the number of cells in the cell complex. So we'll think of n as just like the total number of edges and vertices, right? So this is the total number of cells. We could split this up into the f vector, right? So we'll basically say n is going to be equal to f0 plus f1, fd minus 1. So it's just the whole f vector summed up, right? Should probably write that. All right, so this is a pretty bad data structure. OK. So, all right. But the basic idea isn't so terrible if we could just take this matrix and then squish it down a little bit so that we didn't have to store all of this empty space that was sitting around in it, then it might be OK. And so this is the the next idea, which is basically like a generalization of an adjacency list for a graph, which is that we can just store tables, right? So, and this is probably the one that you'll end up using the most, right? So this is the most common data structure for working with cell complexes. So here's the idea. So we'll say adjacency list, or maybe call it an incidence table. Which is basically, we're going to think of this as a cell list plus fast index for topological queries. All right, so these indexes are going to be static, right? The idea is that what we'll do is we'll just say, well, OK, suppose we want to calculate ij for all different possible cells. Well, there's an easy way we could just build a table that would allow us to answer that very quickly. So the idea is build tables for indexing queries we care about. So here's the concept. So suppose I want to answer I sub j, right, very quickly. So we're going to define this function, which we'll call precalc I, and we'll give it the parameter j and our cell complex x. And what we're going to do is we're going to construct this table, which we'll initially just set as empty, OK? And so we'll loop through all of the faces in x sub j, right? So we'll say for f in the j skeleton of x. Then, well, we know how to loop through all of the lower dimensional faces, which happen to be contained in f. That's a trivial operation, because f is going to be represented as a list of vertices. So all we have to do is just loop through the power set of f, right? So we'll basically say for g contained in f, right? We'll then set the table entry for g. We'll just append f, right? So this is what we're going to do. So we'll basically say, OK, if we think of f as just being some set of vertices, we're going to loop through all of the subsets of this, right? How many people know the easy trick for doing that, right? That you can basically, I'll explain that in a moment. And then when we're all done, we'll just return the table. Let's see, do I have enough time to go into this digression? Not really, no. OK, but here's a sort of pro tip on how to do this, right? So looping through subsets is pretty much the same thing as incrementing a binary counter. And here's sort of the proof of this, is that if you imagine if you have some set like, say, v0, v1. I'll make it concrete. Say we have 4 elements here. This is equal to f. Then we could map, say, a binary number like, say, 0, 1, 1, 0. This would be related to the set v1, v2. So you can just loop through all of the numbers from, say, 0 to 2 to the n minus 1, inclusive. And then that'll just count all of the subsets of this array, right? So the complexity of doing this is, so the cost of initializing this table is basically the vector f sub j times the average size of each of these things, right? Which is going to be basically 2 to the j, right? In the worst case. I mean, if we assume that this is a simplicial complex, it'll be 2 to the j. But it's basically somewhere around that area. And so for d sufficiently small and all of these numbers relatively well bounded, then this is pretty easy to do. I mean, for other sorts of cell complexes, you have to be a little more careful. this technique here is for simplicial complexes, this looping method, right? So I hope that digression didn't make it too confusing, but that's how you do this in simplicial complexes. But OK, initializing this table is essentially a linear operator if we neglect any dependence on dimension and assume that all of our cells are relatively low degree, right? So we can pre-calculate this whole table, store it right here, and then a query is just constant time. We just take the cell that we want to compute the index for, we do a lookup in the table, and then we can just return the incidence list directly from that. So queries are order 1, right? So you can basically take whatever query you want, and you just do one pass over the entire cell complex, and then you initialize the table. Life is easy, right? Unfortunately, updates require building the whole table again. Require table rebuild. And that sucks. So if you have to do a lot of updates over and over again on this thing incrementally, one after another, then this is maybe not a great data structure. But on the other hand, if you're just going to go through and do some batch operation on a polytope, then this is a pretty efficient way to do it, right? And probably the one that you should prefer by default. So if your algorithm, in a sense, requires completely reconstructing a new polytope, like you're going to do some big pass over the entire data set, this is how you should answer all of your topological queries. Shouldn't mess around with anything fancier. But what if you have to do updates? And it turns out we will actually have to do updates because convex hulls in 3D will require us maintaining a cell complex for the boundary of the polytope and incrementally inserting and removing vertices from that convex hull. And these insertions and removals will require us to be able to answer topology queries efficiently. And then we're also going to have to be able to remove and delete cells incrementally. So in general, I don't know of any really great data structures that solve this problem. But in 2D and 3D, there are some really nice tricks that we can do. So this concludes the general purpose data structures for cell complexes. And now we come to the more specialized things that use the weirdness of low-dimensional geometry in some way or another. So, OK. How am I doing for time right now? All right, fine. So OK, so these are now low-dimensional. So the first case is that in 1D, this is trivial. Polytopes just have 2 points. They're just a pair of points, right? So there's nothing to do, right? They're constant size. There's nothing to say about it. Easy. 2D, we've already seen that there are some tricks that we can do in 2D. So in 2D, we know that the boundary of a polytope is actually going to be a polygon. So we can store it as just a list, right? So in 2D, we know that V is equal to E from Euler's formula, right? So we have V minus E equals 0. And we can store vertices in a circularly linked list. And the upshot of this is that we can do neighbor queries in order 1 time. And similarly, removing or adding another vertex is just an insertion into a linked list. So we can also do updates in order 1. So that's really great, like way better than any of these other data structures, and pretty much the way that you should do things if you happen to be working in 2D. So what about 3D? Well, we know that V is actually on the order of the number of faces, but there's actually a lot of extra data that happens to be stored inside a 3D cell complex because we have this connection between these different faces. However, it turns out that 3D polytopes, in addition to obeying all of these additional properties that we have described so far, are actually a good deal more special than general graphs. So it turns out that just not any old crazy graph can occur as the edge graph of a 3D polytope. The neat thing about 3D polytopes is that their boundaries, so if we just look at the graph, is planar. Here's kind of the geometric proof of why this is the case. You take a sphere in 3D, and you draw some polytope on it, whatever, you can just stereographically project this polytope onto a plane by shooting a ray through it. So we can just take any old face, puncture that face, and then unwrap it onto the plane. The resulting cell structure is exactly the same. And so the boundary of any 3D polytope is always a planar graph. And actually, in addition to being a planar graph, it has the other property that it is 3-connected. Or another way of saying this is that it's a series parallel graph, an SP graph. Now, what the 3-connected property means is that if you take any particular edge and you walk around it, you'll basically walk on a face and always come back to yourself. So here's the conclusion of this, is that if I draw some graph like this, then I can just walk along the edges in some cycle, and I will eventually come back to where I started. So we can think of this as that every edge has to live on some face. Right? So the 3-connected criteria basically means that we have just a bunch of these like little face circuits, which are all living together. And so this idea is the basis for probably the most widely used data structure for storing 3D polytopes, which is called a doubly connected edge list, or it's sometimes known as a half-edge data structure. So half-edge data structures supersede earlier and more complicated data structures like winged edge data structures, which maybe you've heard of before. I don't know. But the basic idea here, and I'll draw a picture of how this works. So this is for 3D polytopes. So we're going to call this doubly connected edge list, or sometimes known as the DCEL, or sometimes known as half edge, or sometimes confusingly known as winged edge, although it's not actually a winged edge. I don't know, whatever. This thing has been rediscovered many times, right? It has a lot of equivalent names, but it's a pretty good idea. So here's how this works. So let's zoom in on just a single edge within the polytope. So imagine we have more stuff out here. So we'll call this face F0, this face F1, label this vertex V0, this vertex V1, and this edge E. So here's the idea. So the first concept is that we're going to split each edge in two. And the way that this will work is that we're going to draw one half of the edge going this way, and then the other half going here. So we'll just label each of these things with, say, E, and we'll call this one E prime for the opposite direction. And then for each of these halves of the edge, we're going to store a data structure that will have 3 variables. So we'll call this half edge of E. And for E, we're going to store V1 for the head of this thing. So we'll store a vertex pointer. Which in this case we'll set equal to V1. We'll have a face pointer, which we'll set equal to F1. And we'll have an opposite pointer, which will be a pointer to the opposite edge. And we'll set this equal to E prime. Right? And so similarly, E prime, we'll have this other data structure here. And this thing is going to have a vertex pointer, which will point to the tip of this. And so this will point to the vertex V0. We'll have a face pointer to F0, so the face on the left. And it's going to have an opposite pointer for the edge on the opposite side that'll point to E. All right. So here's how this works. All right. So if we wanted to, say, answer the query of, OK, given a face, enumerate all of the vertices contained inside this face, what we do is we select any edge that's incident to that face, and then we can just walk around this loop. Right. So we can start here. By the way, I should also mention that in addition to storing these data structures for each edge, we store 2 tables. So we also store 2 tables, one which maps vertices to one edge. So each vertex is just storing one edge that it's incident to. And then each face stores one edge. So we have basically a vertex table, a face table, and then we have this list of edges here. Right? That's the idea. So, all right, so let me first illustrate how you use this data structure to walk around a face. So we start from some face f. We locate one of the edges here. From this edge, we can basically find this next vertex. Call this guy v0, right? Or v whatever. That's our edge e. v0 is then going to have a collection of other edges. But what we can do is we can then locate another edge, walking along this way, such that the opposite edge here, this one coming into v, is going to be equal to the tail of this vertex. So we can just walk these pointers until we find the next edge. Then we can walk there and previous. Nope. I forgot one thing. Right. Forgot we actually have to store one other field here. The other one is we're going to store next. Next is going to be this edge here. Let's call this E1, 0. Call this E2. Sorry, I messed this up. Right. Sorry. That's E1. And the next here will be E2. Right. OK. Forgot to mention this, right? Yes, for each edge, we also need to store a pointer to the next edge in the loop here, right? So the idea is that if we want to walk around a face, we get this edge, then we just walk to the next pointer, and to the next pointer, and next pointer, and next pointer, and next pointer, and so on, until we've looped over the entire face incident to this thing. All right, so
how do you still do it though? Like it's like there's you go to the f0 face, or you can go to the f1 face. Why? How do you?
Because each of these, the next edge on this loop has to have the same face incident to it. Right.
Oh, okay.
All right. So that's the thing that makes this work. I hope I'm not over on time here.
That makes sense.
All right. So that's the idea. So each time we walk to the next face, we're going to keep this edge constant. All right.
So then couldn't you just figure that out by, or okay, maybe not. Yeah. Okay.
Yeah. We need to store that pointer. Right. The other thing that we need here too. So now let's say that we have like a vertex. Right. So this is going to have a collection of edges which are going to be incident to v, going in some direction like this. This is what it's going to look like. So here's the basic picture. So if we start from this edge here, which is incident into the vertex, we walk to the next edge. Then we go to the opposite, right? Then walk to the next edge. We can basically keep doing this. So basically, like the face operation, as we just said, E maps to E dot next. In this vertex operation, to walk around a vertex, we go to E maps to E dot next dot opposite. So we basically just keep walking to the next face, go opposite, next face, go opposite, next stage, go opposite, and so on. And if you do that, you'll just walk over the set of all edges which are incident to that vertex. All right. So the upshot of this is that we can answer any incidence query from, say, edge to edge, or edge to vertex, face to vertex, vertex to face, by basically doing one of these sequences of pointer traversals. And inserting and removing elements from this data structure is also pretty easy, because it's just moving the pointers around in these data structures. So you can view this as just delete a pointer and swap it, right? It's also really easy to do something like, say, calculate the dual of one of these data structures, because all that you have to do is just switch the vertex and face pointers and then update the next, right? And then everything just remains completely the same. So you can do a dual of an entire half-edge data, or of an entire doubly connected edge list in order n time, and you can answer any query on it in order 1 time, and you can do any update in order 1. The cost is that you have to keep all of these pointers around and then do this extra mess. So in this setting, it would seem like this is always the data structure you should use for 3D. But in reality, the only time you really need to do it is if you actually need that constant time update. And the reason is that, well, this ends up being pretty efficient in sort of the asymptotic sense. in practice, because there's all of these pointers sitting around here, it tends to have fairly poor locality of reference. So you're always going to be doing a bunch of pointer arithmetic when you're jumping and walking through all this stuff going on here. So really, if you're just going to be doing some bulk operation, you should probably stick to that incidence table approach. Otherwise, you can use this. And I think I'm just about out of time here, so I think we better stop at this point.